Hello, welcome to this video on heap sort. Glad to have you here. Today we are going to delve into how heap sort works, as well as its advantages and disadvantages. And we'll also be comparing heap sort to other sorting algorithms. But before we get to the actual algorithm, I will provide a conceptual overview for those of you who are entirely unfamiliar with it. However, for those of you who are quite familiar and clicked on this video for a refresher on heap sort, you can skip over using the timestamps that will be provided in a second. So here is a list of topics I'll be covering today. First on the list is trees. I will be going over some basic tree terminology here. Then I'm going to talk a little about binary trees, which are a subset of trees. And I'll talk about their properties and other types of binary trees that exist. And then we'll discuss heap data structures, like how to create heaps and all that. And we'll finally get into the actual heap sort algorithm. And again, the timestamps are there for you to skip over to more unfamiliar topics if you wish. So yeah, let's get started with our first topic, which is trees. So the tree data structure is a set of nodes that are represented or identified by keys. For example, if you look at this purple node here, it has a key of 11. And nodes can be connected to other nodes, which leads me to the defining property of trees. All trees must be arranged in a hierarchical manner, much like a family tree. So an example here, our purple node would be the parent of nodes 5, 81, and 39. Which are trivially the children of the purple parent node. And this hierarchical structure can continue, much like how our children may have children of their own one day. Now, adding to this, there are further definitions built on top of parent and child node definitions. First of which is the root node, which is the highest node in the tree, and it has no parent node. Next, the internal nodes are nodes that have one or more child nodes. And finally, the leaf nodes are nodes with no children. Now, the most important question to ask is why we use tree data structures. Well, data structures like arrays, linked lists, stacks, queues are linear, but the tree data structure is one of the non-linear ones. Therefore, when we need data to be structured in a hierarchical way, or when we need to perform quick inserts or deletes or searches, trees are the way to go. So there are many other types of trees, like the binary search tree or the AVL tree or the B tree. And I know you all are yearning for more of my colorful commentary on these trees, but I will reserve these topics for future videos. But what I will go over today is the basic concept of binary trees and the types of binary trees. So we all are aware of the by prefix, yes. We see these prefixes used in our everyday language. So the by prefix indicates that there are two of something. Keeping this in mind, I will provide a definition of binary trees. A binary tree is a tree in which we enforce a maximum two-child policy on all nodes that belong to the tree. So, super quick example, let's say 28 is a node of a binary tree. If we give it a child, like so, it is still a binary tree since the node has only one child. If we give it another child, like so, it is again still a binary tree since there are two children. But if we give it another child, it is not a binary tree anymore because the node now has more than two children. Pretty simple. Let's take a slightly bigger step and look at some other types of trees within the context of binary trees. I'm going to talk about three types of trees: the full tree, the perfect tree, and the complete tree. Let's first quickly go through their definitions. So a full binary tree is a tree where every node other than the leaf nodes have two children, meaning each node has two children or no children. A perfect binary tree is a tree with all its leaf nodes at the same level, and all nodes have two children. A complete binary tree, which I think to be the most elusive of the three, is a tree in which at every level, except the deepest, is entirely filled from the left. So let us learn by example and take a look at this simple tree here. This tree is full because every node that is not a leaf has 2 children, and it's perfect because all leaf nodes are at the same level or height, and it's complete because nodes are completely filled from the left without skipping. As you may have caught on here, all perfect trees are full and complete by definition. Now, let's give node 3 2 children. This would make the tree a full tree, but not a complete one because it is not filled entirely from the left. And it's not perfect either because all leaf nodes are not on the same level. If we were to give node 21 2 children, then now the tree would become perfect, thus full and complete as well. Now if we take away the 2 children of node 3, then the tree becomes full and complete, but not perfect. Next, if we were to take away the right child of node 21, the tree would just be complete because each node does not have exactly 2 nodes. Now, I mentioned briefly that one of these trees is quite elusive when it comes to grasping conceptually, and that is the complete tree. Understanding complete trees is crucial to understanding heaps, so let's carefully dissect complete trees. Then we can move on to heaps and heap sort. First, understanding how to represent a tree from an array is crucial to understand how the heap works. Let us start with an empty array and insert elements one by one. Above this array, I will display the complete tree representation as each element is being inserted. The index number of the corresponding array element will be indicated below the node. So I will insert a total of 6 elements, and I implore you to focus on the order of the elements that are being inserted into the tree. So 37 is the first node I'll be inserting, then 21, then 3, then 13, 5, and lastly 20. Did you notice the way the elements were being inserted? So the dotted line indicates the order the elements are inserted into the complete tree representation. So we can represent an array as a complete tree in this manner. So how would we know, say, the left child of node 37, the root node? Complete trees have an interesting property that can help us perform useful functions. And this relationship between array and complete tree elements and their indexes can be represented with 3 basic equations. Before anything, we would need the size of the array or tree, which in our case is 6. And given that we are working on the node at index I, to find the left child of that node, we would use the equation 2 times I plus 1. To find the right child of that node, we would use the equation 2 times I plus 2. To find the parent of a node, we use the equation I divided by 2 minus 1. So one quick example. Let us find the right child of node 21 at index 1, and we find that with 2 times 1 plus 2, which equals to 4. And the node at index 4 is node 5, which is in fact the right child of node 21. Now, we finally will be moving on to the heap data structure. The reason I deliberated on complete trees so much is that heaps are a form of complete trees. Heaps are complete trees that satisfy one of the 2 heap properties, and those are the max heap property and the min heap property. Because the min heap property is the reverse logic of the max heap property, we are going to be focusing on the max heap property only. So the max heap property states that any node must have children with smaller keys. This also means that the root node of a max heap has the largest key out of all the nodes. And in a min heap, the root node would have the smallest key out of all the nodes. Look here at this very simple tree. We can see that 1, the root node is clearly not the max, and 2, the root node is smaller than both its children. Now we are going to try to make this tree into a heap, a max heap, or in other words, we are going to try to heapify from the root element. So let's heapify at index 0. Initially unaware of its children's potential, node 3 here exhibits its big ego and deems itself the largest. Node 3 then notices its left child, node 21, which to its sadness is greater than 3, so we crown node 21 with the maximum title. Next we check node 37, the right child, which happens to be the bigger, badder sibling of node 21. This node with its Herculean build usurps node 3's precious position as parent and root of this tree. Defeated, node 3 takes its rightful place at the end of the tree, not even half the node 37 is. Next, I'm going to talk about two ways of creating a max heap. First, I will create a max heap from a given filled array of numbers. The second way of creating a max heap is by inserting elements into a heap and checking whether the heap properties are satisfied during the insertions. So, the first way, let us create a max heap from an array. The first node we want to start with is the last non-leaf node, which can be found with the equation the floor of n divided by 2 minus 1. So in our case, we would want to start with the node at index 2, which is node 3, and let's call heapify at this index. Because 20 is greater than 3, we swap the nodes, and we would want to continue this until we reach the node at index 0. So let's now call heapify at index 1, and because 58 is greater than 21, we swap the nodes. Now, let's heapify at index 0, and because 58 is greater than 37, we swap the nodes. And finally, the max heap's now complete. Next, let's try to create a max heap by inserting elements into an empty array. Let's start with inserting 37, no parent, so we continue. Then we insert 21, and because 37 is larger than 21, no swap occurs. Now let's insert 3, and 37 is greater, so no swap. Insert 13, which is less than 21, so again no swap. Insert 5, no swap. Up until now, this must look nearly identical to inserting elements into a regular complete tree. However, let's now insert 100, and because 100 is greater than 3, we swap the nodes. Once again, 100 is greater than 37, so we swap again. Now we can verify that this array representation of a max heap satisfies the heap property by checking that each node has children with smaller keys. We can also verify that the max heap building worked, since 100 is in fact the maximum of all the keys. More on heap operations and related topics like Dijkstra's or priority queues will be detailed in later videos. Now that we got all that out the way, we can start with heap sort. Well, technically, creating a heap is the first part of heap sort, so let's start with the next part, which is the actual algorithm. As you can see here, we have a max heap that adheres to the max heap property. Using this max heap, we will use the heap sort algorithm to sort the nodes in descending order. If we want ascending order, we would use a min heap instead. One big advantage of heap sort is that it's relatively simple in concept and implementation, as all we need to keep track of pretty much is the array size of the remaining unsorted numbers. In our case, we have to keep track of the array size of 6. We start off the algorithm by swapping the root element, the element at index 0, and the last element, the element at index n-1. Note that since the largest number of the tree is at the root, essentially what we are doing is we are swapping the biggest element with the smaller element. Next, we want to decrement the size, which now equals 5. This act of decrementing means that we will be building the sorted array from behind. Then our next step would be to heapify from the root at index 0. And since node 3, of course, is punier than node 21, we swap. And we continue on and Sparta kick node 3 down another peg because it's smaller than 13. Because we do not have to perform any more heapifies, this marks the end of the first round of the algorithm. From here, we would want to continue swapping the first and last element until the size reaches 0. So starting off the next round, we swap 21 and 5, and heapify again. And when we reach size 0, we end up with a sorted array. And I encourage you to rewind the video and rewatch the algorithm while keeping in mind these 4 steps of heap sort. First, swap the first and last elements of the array, then decrement the size, then heapify from root, or the index 0, and then continue till the size reaches 0. I know it's tempting to close this video now, but I implore you to stay around just a little bit longer, for I need to pose to you an absolutely crucial question. If I could just find the slide. Yes, here it is. Why? Why should we use heap sort is the question. And being the ultimate bringer of innovation, I will answer this looming question in the most innovative of formats. A pros and cons list. So here it is. So the first pro is that heap sort is guaranteed O and log n performance in terms of time. So if you require a program that needs sorting done in that required time in a guaranteed manner, then heap sort is the way to go. It is also O1 space complexity, meaning that it doesn't use extra space. And compared to sorts like merge sort, while it is quicker than heap sort, it uses extra space, so there's that kind of trade-off between the two sorts. Another pro is that it has a hierarchical structure inherently, so if you require arrangement of data in a hierarchical manner, then heap may be a good option. Another advantage of heap sort is that while sorting, if heap sort is interrupted for some reason, the output array is still somewhat sorted, which might be relevant in some scenarios. And lastly, finding the min and max is very, very quick, so if you need a program that requires that kind of function, then heap sort may be your answer. Moving on to the cons of heap sort, it's not able to handle complex data that well. If you're working with complicated forms of data, then heap sort might not be the greatest option. Heap sort is also unstable, meaning that it switches the relative order of duplicate elements. It's also non-adaptive, meaning that giving it a almost sorted array doesn't make the performance faster. And the last and one of the bigger disadvantages of heap sort is that it is cache inefficient, and compared to its cousin quicksort, it has poor locality of reference, which makes it slower than quicksort. Also, a quick tidbit. My main language is C++, so if you code in C++, the sort function is actually an algorithm called introsort or introspective sort, which is basically quicksort that switches to heap sort upon reaching a certain depth of recursion. So maybe in a future video, if you want, I can show you all the inner workings of this sort. If not, that's fine too. But that's all I have for heaps and heap sort today. Thank you all so much for watching my video. I hope everything was clear and easy to understand. I do have other videos in the works, so it would be great for you to come back and check them out, and maybe subscribe if you like what you see. It was genuinely great having you here, and until next time,